These are the notes on balancing and writing chemical equations. This video is going to cover the first part of these notes, which is just going to be on balancing chemical equations and basics of chemical equations. All right, we have talked about counting the number of each atom in a molecule before, but just as a reminder, as we're looking at this, when we're looking at a chemical, we can separate the elements based on looking at for those capital letters. And because some of our atomic symbols have 2 letters, some of them have 1, those separate out based on the capital letters. So we have lithium, we have sulfur, and we have oxygen. So for those, the number of each element, well, if there is a subscript right after an element, that tells us how many we have. If we don't have a subscript written, it is implied that that's a subscript of 1. And then oxygen, we would have 4 atoms of that. So this molecule or compound is going to have, if we want to find the total, we would add all of those up. So there would be 7 atoms in this molecule. Looking at number 5, NH4Cl, we don't often see carbon and iodine together. One thing that's a little tricky is that a lot of times a capital I without the kind of serifs, the top and the bottom, can look a lot like a lowercase l. And so if we have an I, it will have kind of the top and the bottom of it. And it won't normally be with a C. So anytime you kind of see that Cl, that's often our element chlorine, and not carbon and iodine with that. So this one we have nitrogen, that's a capital, hydrogen, capital letter, and then that capital C, and then that kind of Cl with it. So we have 1 nitrogen, 4 hydrogens, and there's 1 chlorine in this. Feel free to look at number 6 on your own. Looking at number 13, if now we have parentheses, we can still look at our different elements. I have calcium with that capital C, lowercase a, phosphorus, and oxygen. We have 3 calciums in this chemical or in this molecule, but anytime we have these parentheses, that means that that subscript is going to distribute to both of those pieces in there. So if I have 1 phosphorus inside the parentheses, that means that 1 times 2, I'm going to have 2 phosphorus total in that molecule. For my oxygen, 4 times 2, that would be 8 oxygen, so this would be a total of 13 in that molecule. Feel free to look at 6, 14, and 15 on your own. The answers are on the next page, but if you're comfortable with that, feel free to continue on in the notes with me. All right, so we talked just a little bit about subscripts just now, those little numbers at the bottom. And so those subscripts, if you kind of look at our picture at the bottom here, that subscript, those are the numbers that we're using when we're writing our formulas. And so what determines the subscript in any given chemical formula? Well, it depends on what compound or molecule is formed. If we have something that is ionic, that means that we are going to use our charges, and we do that drop and swap because it needs to be a neutral compound. If it's covalent, we are going to use the prefixes in the name for that molecule. And so all of that's based on what we talked about in our chemical bonding unit. So needing those charges or those prefixes if it's covalent and those are sharing electrons. And so how do subscripts change from the reactants to the product? Well, they are going to change based on what they're paired with. And so if we look here down at the bottom, hydrogen and oxygen are both diatomic, which is why we have that H2 and that O2. But in our H2O, that's covalent, that's dihydrogen monoxide. We only have 1 oxygen because it is now paired with that hydrogen. When these were alone, they had to have those subscripts because they are diatomic. And so what compound is formed, I guess we could also say up here in this first question, though we do have to pay attention to our diatomic elements on our periodic table. Do you ever change the subscripts for any formula in the chemical equation while balancing? The answer to that is no, because the subscripts depend on the compounds, not on the reaction as a whole. So it depends on the compound or the bond that's formed. That's why we need to balance a chemical reaction, is to then say, okay, how many of each do we need in order to get whatever we're starting with in our reactants? We need to have that same number. I have 4 hydrogens over here. Well, I need 2 times 2. I need 4 hydrogens here. I have 2 oxygens here. I have 2 times 1, 2 oxygens over here. What effect did adding a coefficient have on the number of atoms in a compound? So if we look at an example, if we have CH4 versus we put a 2 in the front, well, that coefficient is going to distribute to every element in our compound. So the coefficient distributes to all elements in the compound that follows it. And so this 2, we would have 2 times 1. So this means that I would have 2 carbons, 2 times 4, and 8 hydrogens if I am counting those up. All right, so some of this should be review from when we were looking at the balancing chemical equations, or sorry, we are doing the balancing chemical equations notes. So we are going to be looking at kind of this idea today as we look at balancing. All right, so what does it mean to balance an equation? So when a chemical reaction occurs, no atoms are created or destroyed, they are just rearranged. So that is one of our fundamental laws, the conservation of matter. The amount of each element on the left side, which are the reactants, the things that are reacting, must equal the amount of the same element on the right side, the products. And so that's kind of what I was talking about up here, that we have 2 times 2, we need 4 hydrogens on the left and 4 hydrogens on the right in order for this to be balanced. Same thing, 2 oxygens and 2 oxygens in order for that to be balanced. You do need to know reactants and products. Those are our 2 keywords. So any chemicals that are on the left side are our reactants. The things that are reacting, products, that's what gets produced after the reaction. A tip to help you remember that is RAP, reactants, arrow, products. So if that helps, that arrow there is separating our reactants and our products. So for chemical reactions, we do have some vocab. We've got these chemical formulas, and we use symbols instead of words to summarize our reaction, because those symbols, it's kind of like a math equation. Those are easier for us to work with. And so we have our chemical symbols, so carbon and hydrogen. Those numbers that are in front are called coefficients. The arrow, we might, if we're reading that, it might read yields or produces or forms or makes. So that's kind of telling us where our reactants are going to be separated from our products. We have our full formulas for our compounds, and we also have our subscripts. And so our reactants, those things on the left, what we're starting out with, these are being changed through the chemical reaction. And then our products, those are what we're going to end with. That's why they're on the right. We read left to right. And those are the things that are formed or produced in that chemical reaction. And so again, comparing to reading a book, we read left to right on the story. And so left to right, same thing here as we're looking at these reactions. All right, so here's again some of that more vocab, those coefficients, the numbers in front, subscripts, those smaller numbers there. If that helps, kind of read through those a little bit more. So what makes an equation balanced? So an equation, a chemical equation, means if we have kind of these individual compounds, the plus means we're going to combine them. If we have that arrow, just like an equation in math has an equal sign, an equation in chemistry is going to have that arrow instead, where we have chemicals on the left and on the right. And a chemical equation is considered balanced when the number of atoms on one side equals the number of atoms on the other side. So if we look in this one, it's different than that example that was up above, because now we have H2O on the left. If we don't have any coefficients here, H2O, we have 2 hydrogens and 1 oxygen. H2, because hydrogen's diatomic, we have 2 hydrogens, and O2, also diatomic, 2 oxygens. Because our numbers of oxygens are not equal, that means that this is not a balanced reaction. We can get that to balance by changing our coefficients. Each of these right now had a coefficient of 1, and when they had a coefficient of 1, it wasn't balanced. So we can change one or multiple to get those balanced of changing those coefficients. And so if we look over here, this one has a 2 in front of that magnesium, so that 2 times 1, 2 magnesiums. We have a 1 in front over here, 1 times 2, 2 oxygens. If we look on the other side then, this 2 here, each of these has a 1. 2 times 1 is 2. Our magnesiums are equal. Our oxygens are equal, which means that this is a balanced reaction. So our focus on today, since we already know how to write compounds, is that we are going to work on, and we know how to kind of do some of these individual pieces. We're going to look at what if we take all of these and we balance that chemical equation. And there are some steps here. And I'm going to expect you to show some work. You might not show your work exactly how I do, but how I do it is I draw a line under the arrow to separate the sides. Again, that arrow is kind of like our equal sign if you think of this in terms of math. And then draw out the elements you have on both sides, or I guess I write them out. Count how many of each you have to begin with. And then we add coefficients of substances so that the number of atoms on the left, the reactants, is going to equal the number on the right. And we put coefficients in front of each substance to indicate how many you have. You want the smallest whole number coefficients as possible. They have to be whole numbers. And if something doesn't have a coefficient written, that implies there's a coefficient of 1. And we really just don't write 1 coefficients. You might be asked to put a 1 in if you are doing kind of a fill-in-the-blank test, but we usually leave those blank, and that represents that we have 1 of something. All right, and then here are some hints. Again, listing the number of atoms we have, picking one element to start our balancing first. Once that one's balanced, then move on to another one. And balance elements in a compound first. That means those things are going to affect other elements. We save things that are by themselves for last, especially hydrogen and oxygen, just because those are going to have impacts on other pieces. Our diatomic elements, remember those. So when they're alone, they are going to have that subscript, and so that is going to change kind of those totals. If those are in a compound, though, we need to follow our rules for writing our compounds. We're going to get to writing these in the second part of the video. So let's focus on balancing. This one is written out for us. We have lead combines with sulfur to produce lead sulfide. As I'm looking at this, my first step, I put a line right underneath, and then I go through and I just usually will list left to right. So lead and sulfur, and then my order might change on the other side, but I'm going to keep whatever order I wrote on the first side just so that I can easily compare across my line. Now I'm going to list how many I have. Well, Pb, if I don't have a coefficient there, that's just 1. Sulfur, I also just have 1. And then in my compound, 1 and 1, because as I compare, my leads are equal, my sulfurs are equal. This is actually already balanced when we have coefficients of 1 for each. And so this one, we don't actually have to add any coefficients in. That one's balanced, so we can leave these lines blank. Those blank lines do represent values of 1. We just, as scientists, get lazy, so we don't write those in. All right, now let's look at another one. This one, we have potassium nitride on the left, and then it produces potassium plus nitrogen. So I've got potassium, and I have 3 of those. Nitrogen, I have 1 from that subscript. And then potassium and nitrogen. I have 1 potassium and 2 nitrogens because nitrogen is diatomic. Now when I'm looking, comparing, well, I have 3 potassiums on the left, 1 on the right. We can't get rid of any potassiums because this is formed based on those charges for each of those. So that means I need to get this 1 up to having 3. And I can do that by adding a coefficient. And so if I put a 3 here, that means I'm going to have 3 times 1, 3 potassiums, and now those are going to be equal. What that kind of looks like is that 3 in front is the same as me saying, okay, I have 3 of those potassiums, just like I have 3 here. But instead of writing that K plus K plus K, that's why we put that coefficient of 3. It just simplifies everything out for us. Now those are balanced. Now let's go to our nitrogens. Well, I have nitrogen. I have 2 on the right. Sorry. Yep, 2 on the right, 1 on the left, which means I'm going to need a 2 here. Well, putting a 2 here in front of that term with nitrogen not only impacts my nitrogen, 2 times 1, so that now these are balanced, but it is also going to go 2 times 3. Now this is 6, so that means that my potassiums aren't balanced anymore, which isn't a problem. We can just go back and say, okay, well, we actually need 6 instead of 3. I have a 3 right here. How can I get 6? Well, I'm going to actually need a 6 in front. And so then that 6 times 1 is going to give me the 6 I need, rebalancing that potassium. Depending on where you started, you might not need to do both those steps. If you started with your nitrogen, you maybe didn't have to balance that potassium twice, but it's not a problem that we had to do that. So our final reaction then is 2 potassium nitrides produce 6 potassium plus 1 nitrogen, N2. All right. This reaction has a little more in it, so it looks a little bit more complicated. As we're looking at this one, we're just going to have more things to list. I just start at the left. So iron, I have 1, Cl, and again, if we have this with a metal, it's generally going to be chlorine, not carbon and iodine. So chlorine, we have 3. Into my next compound, sodium, I have 1. And if I notice that I have an OH on both sides, and that's one of our polyatomics, our OH minus 1 is hydroxide, then I can actually keep that group together. And instead of just saying, separating the O and the H, I can keep that OH group because the group stays together on each side. So then I'm just looking at how many of the group do I have. I have 1 OH group on the left. I'm going to copy these in, especially a reaction like this. Those our pieces are going to reorder, and so this way I can just compare across my line. Iron, I have 1. OH, I now have 3, because that 3 is outside the parentheses. Sodium, I have 1, and chlorine, I have 1. It doesn't matter where we start. I'm going to start at the beginning. My irons are balanced. I'm not going to do anything. Chlorine, I have 3 chlorines on the left, 1 on the right. So I need to get this one up to 3. I can do that by putting a 3 in front of my term with chlorine in it. That means I'm going to have 3 times 1 for my sodium and 3 times 1 for my chlorine. And now that one is balanced. Looking at my next term, sodium, I've got 1 on the left, 3 on the right. So I can put a 3 in front. I need to put a 3 in front of my sodium here. 3 here. That means 3 times 1. There's my 3 sodiums. Those are balanced. That also now means I'm going to have 3 hydroxide groups. And that works out perfectly by balancing those hydroxides as well. 3 and 3. Just checking back, my iron didn't get impacted by any of those coefficients. And so then that is done. So we have 1 FeCl3 plus 3 NaOH produces 1 Fe parentheses OH3 plus 3 NaCl. Notice I didn't change any of my subscripts. I'm just adding coefficients so that it is balanced. All right, example 4. KClO3 produces KCl plus O2. So chlorate is a polyatomic, but if we notice here, ClO3 gets broken up over here. So this is one where we are going to break up that polyatomic because we don't see that group KClO3 on both sides. So I'm going to split this up into my potassium. I have 1. Cl, I have 1. Oxygen, I have 3. So using our subscripts, keeping my same order on the other side, I have 1 potassium, 1 chlorine, and 2 oxygen. My potassiums are balanced, my chlorines are balanced, but my oxygens, I have 3 and 2. There's nothing I can multiply one of these by to get the other number, but if we think of what is a least common multiple, what is a number 3 and 2, we can multiply both of them by to get something to be the same. Well, I could multiply by, to get 6. And so if I put something in front of my KClO3 to get 6 oxygens, then I could get my oxygens on the other side to match. So let's put a 2 in front over here. That is going to impact my potassiums, my chlorines, and then my 2 times 3, my oxygens. But then on the other side, I can, to get 6, I can put a 3 in front here, and that 3 times 2 is going to give me the 6 oxygens in order to balance that out. We do have to go back and do an initial check because these two did change, which means we now need to get these balanced. I have 2 potassiums on the left now, 1 on the right, and so I need to put a 2 in front of my potassium chloride. 2 times 1, that's 2 potassiums, 2 chlorines, and then my potassium and chlorine balance as well. You don't need to show maybe as much work as I do. This helps me stay organized. You do need to show some work though when you are going through and balancing problems on an assessment. All right, this is our last one of just balancing, so the last one of this video. This type of reaction is the one that I find the trickiest to balance, just because of how we have oxygens in both of our products, but only one of our reactants. And so we've got carbon 3, hydrogen 8, oxygen 2, and then I'm going to have my carbon, hydrogen, oxygen. As I look at this though, I've got my CO2, so I have 1 carbon and 2 oxygens. And then my H2O, I have 2 hydrogens and I have another 1 oxygen there. I like to write these out and separate my oxygens on the bottom into the 2 and 1, because if I put a coefficient, it's only going to change one of these. And then I like to do the total off to the right. Now let's start balancing. I'm going to look at balancing my oxygens last because I have oxygens in both of these terms. And so I'm going to wait to see what I end up with before I do anything with my oxygens. Starting with my carbons, I have 3 on the left, 1 on the right. Well, I need to increase this to get to that 3 because we can't simplify our compounds. They're written based on our rules of writing chemical compounds. So if I need to get up to 3, I can put a 3 in front of my CO2. That means I've got 3 times 1, 3 carbons, and then 3 times 2. That only affects the 2 oxygen I previously had. And now I can update my total. 6 plus 1. Now I have 7 oxygens total. My carbons are balanced. Next, let's look at our hydrogens. We have 8 on the left, 2 on the right. Well, I can multiply 2 times 4 to get 8. So let's put a 4 in front of our term with the hydrogen. 4 times 2, that's 8. 4 times 1, that means that only the 1 in my oxygen totals is changing. 4 times 1 is 4, and then I'm going to need to re-add these together to get 10. Now my hydrogens are balanced, so the only thing left to balance is my oxygens. I need to look at my total over here. I have 10 oxygens on the right, 2 on the left, and so thinking of, well, what coefficient can I put? And I would need a 5 in front of my O2 to get that 5 times 2, 10 oxygens, and to balance those out. All right. You're going to, these notes will finish in part 2 of the video, which is on writing chemical reactions. Reach out to your teacher on balancing if you have any questions.